with our external forced convection. In the previous discussion, we have discussed about the scaling analysis on the flat plate for the energy equation, right? And that was done for uh, the Prandtl number much less than 1, that is delta much less than delta t. And here we consider that u is almost equal to u infinity for everywhere in the delta t. Everywhere it is not exactly everywhere, but for the 80% domain under the thermal boundary layer that we considered. So now let us look the case where the Prandtl number is much greater than 1, and that is delta is much greater than delta t. So now if we draw the case, so again this is my flat plate, okay. I always try to draw the figure so that it looks good, okay. I mean, because then your brain will try to, I mean, then your brain will say that it is something that on which I am interested. So I always suggest that whenever you are solving something, even in rough, try to make it as clear as possible, okay. Then your all analysis will be, I mean, clutter free and good. So now let me draw the first. So this is the fluid, incoming fluid having u infinity and t infinity. So maybe this is the hydrodynamic boundary layer. So yes, this is the hydrodynamic boundary layer. This is delta, okay, and delta is greater than delta t. So delta t will be something like this, right? So this is delta t. So now you see that uh, the domain inside the thermal boundary layer edge, that is also inside the velocity boundary layer edge. So u infinity prevails here, right? U infinity prevails here. So by no means you can say that here inside the thermal boundary layer you have the velocity u infinity. So this is the main difference between the previous case and this case, okay. So here this assumption will not work, that u is equal to u infinity for all y, that is belongs for y belonging to 0 to delta t. So this assumption here it will not work, right? Here it is wrong. So let us now see that then what assumption we will take. That is, now the main task is what will be the velocity scale, right? Okay, what will be the velocity scale inside the thermal boundary layer? This is our question. So here we take an assumption, that is the velocity, the so the velocity scale, yeah, so u infinity is the velocity scale for the hydrodynamic boundary layer, okay. Then what will be the velocity scale for the thermal boundary layer? Here we assume it to be a linear variation type. So uc e by u infinity is equal to delta t by delta. So here we get the uc as delta t by delta into u infinity, okay. Okay, here it is like that. If you consider, I mean, this is a very rough approximation type, that is if you consider it to be a linear profile, then here it is u infinity, right? So you are, so if this is a scale y and that is inside the delta t, then if it is linear, so then what will be the velocity here? It will be y into u infinity by delta, okay. And this y has the order of magnitude of delta t. So this is the type of intuition here, okay. And as these scales are very small, that is why we can do this approximation, okay. So this is the crux of the scaling analysis here. Okay. Now let us do the same analysis that we have done earlier. So by this time, if you have revised, then you should get habituated. So I always see this thing that most of the students, they what they feel and what they do, that uh, so I am giving you two examples. Okay, so let me talk about the heat transfer and the the electrical networks. So students still face problem to visualize the heat transfer networks at the electrical networks. So what my point is, there are very mathematical techniques that are same for the different different physical phenomena. Okay, but you should take a mindset in which your your task will be easier. That is, you know that if I have problem 1 and problem 2, and by now you know that problem 1 and problem 2 has the same approach. Okay, problem 1 and problem 2 are having the same approach, and but your mentality is still is your mentality is still stuck in a place that I know the solution of problem 1, that is to be done by this method, but the same method is applicable in problem 2. The mathematics is same, but still some students fail to get that. Okay, and that is just because of your mentality. You see a problem as a mathematical problem, as an individual problem, but that is not the thing. You should learn from each problem. That is, if I face a similar problem even in another subject, then also I should be able to crack it. Okay, so for that I will now go a bit faster. Okay, because I have told the similar approach just in the previous lecture. So let me write now the continuity. So del u del x plus del v del y, that is equal to 0. So this is the continuity, right? And it is having a scale of uc, that is delta t u infinity by delta. It is having the scale of vc by delta t. So why delta t? Because we are concerned inside the thermal boundary layer. So that means Vc is of the order of delta t square u infinity, right, by delta. Okay. Now let us write the energy equation. Okay. So energy equation is what? For steady state, u del t del x plus v del t del y, and that is equal to alpha del square t del x square or y square. And now I am not telling the logic because I have explained it earlier, so you should get it, right? So now if I do the scaling here, then I know that u, so this term will be what? Uc, that is delta t u infinity by delta, okay, into some tc by L, that is the scale for x. Now Vc is what? Delta t square u infinity by delta Tc by delta t. So see that delta t and delta t cancel out, and the whole LHS is of the order of delta t u infinity Tc by delta into L, right? Okay, so now this term alpha, this term is the scale of alpha Tc by delta t square, right? Have I done it correctly? Because here there is no L, right? So let me check it. Okay, so here we have made a mistake. That is, here this was the scale for u, so and for the x I have to include L here, right? So Vc should be this by L, and here also it should be a by L, and now it is correct. Okay, so and this is the scale for RHS. So RHS scale should match with LHS scale, So delta T by U infinity by Tc delta into L is alpha this by this, right? So we have to get the delta T, right? So delta T whole cube by L is equal to delta alpha Tc by Tc by U infinity. So Tc and Tc will be cancelled out, and let us multiply what, um, okay, so let us multiply L square in the both side, 1 by L square. So this will be L square U infinity, right? Okay, now this we can modify. So we can, now we know this delta, the scale of this delta, that is what, that is L by REL whole to the power minus half, that we have done previously. And we also now write this alpha as alpha into alpha by nu into nu. So this is my 1 by Prandtl number, right? And also I can do maybe one more thing, that is, okay, so now this expression then becomes what, L by REL whole to the power minus half, alpha means nu by Prandtl number, okay, into 1 by L square into U infinity, okay. So and Reynolds number is what, Reynolds number is U infinity L by nu, right? Okay, so if I want to get that, then what I have to do, so I have here U infinity L by nu, but an extra L is coming, right? So what is the catch here? So there is an extra L. Why that extra L is coming? So let me see if there is any mistake. Let me see. Because this term, you see that this becomes, okay, no extra L is coming, this L and this L is cancelling out, and I apologize this for this silly mistake. So here it becomes uh, and there also I have done a mistake, okay, because delta is scaling with L whole to the power REL whole to the power minus half. If it is 1 by, then it will be plus half, okay. So then it will be 1 by REL whole to the power half into 1 by, see this, I can drop this nu here, right? And this will be U infinity into L by nu, and that is nothing but my REL into 1 by PR, right? So that becomes my PR to the power minus 1, REL to the power minus 3 by 2, right? And that is nothing but delta T by L whole cube. So my delta T becomes L into PR to the power minus 1 by 3, REL to the power minus 1 by 2, okay. And similarly now I have to find my Nusselt number, okay. So my Nusselt number will be NUL, that is HL by K, and now I know H delta T by K into L by delta T. I have shown earlier that this becomes of the order of 1, okay. So that means it becomes of the order of L by delta T, and that becomes what, PR to the power 1 by 3, REL to the power half. So this becomes the order of the Nusselt number, okay. So NUL becomes PR to the power 1 by 3 and REL to the power half, Okay, so now we have the two expressions for Nusselt number for two cases. Okay, so now we will do the exact analysis. We have done the order of magnitude analysis. Now we will do the exact analysis, and that is given by the similarity solution as we have done in the momentum. Uh, I mean, for the momentum equation. Okay, similarity solution for energy equation over flat plate. Okay, so if I now do that, so just recall the procedure that we have I have described you, that how to arrive at the similarity solution. Okay, so and that is why I was telling that I have already completed the similarity solution for the momentum. The same philosophy is here, so you should not ask that now what I should do. I mean, obviously the approach may be different, I mean the similarity variables, but what is the philosophy of the similarity solution, that you should ask yourself. So now pause the video and ask yourself that what is the what is the philosophy of the similarity solution. That is, if in any interview someone asks you that what do you mean by similarity solution, so he will not ask you to do similarity solution for a problem, but he can ask you this. Okay, so now the answer is what, that is we know that we can convert the PD into OD by defining a similarity variable, and there exists a single graph, that and that graph will be of that similarity variable and a function of that similarity variable, and that graph will represent all the graphs, all the graphs throughout the domain. That is the similarity solution. And mathematically, if I can define a similarity variable for which the problem becomes from an PDE to an ODE, if that is happening, then I can say then I know that yes, my similarity solution exists. So all these things I have explained in the similarity solution for momentum equation. If you have forgotten, then I would suggest you to go through that again. Okay, now similarity solution for energy equation. Okay, so I told you that there are two methods. One method I have shown there, that uh, I did not assume the similarity variable earlier. Okay, but I had a intuitive idea. But here I will assume some similarity variable. By this method, I am showing you both the ways. Both the ways actually are same. They are converging to the same thing. But previously, the form of the exact form of the similarity variable, that came from the solution itself. So your homework is to apply the same thing here, and I am doing the opposite thing here. That is, I will assume the similarity variable beforehand, and you have to prove that that form will be the actual form if you go by the previous method, that is not assuming any previous profile, right? So now let us proceed. So let me first write the energy equation again. It is U del T del x plus V del T del y is equal to alpha del 2 T del y2, right? So you see that we need U and V both. Okay, so the similarity solution for U and V were like this. So U was, okay, sorry, so U by U infinity, that was F dash, right? And V was this into U infinity nu x eta F dash minus F. Okay, so I think I have derived the form of V. If I have not derived the form of V, then you can easily calculate it from the continuity equation, that is del U del x plus del V del y is equal to 0. From here you can easily calculate the form of V. Okay, just write this in terms of F and eta and then integrate, right? So if I have not done this, then it is your homework. So now onwards, you should practice these things by yourself. And if you are not able to do this, just if I get at least one comment that I am not able to do this, then I will solve it in my next lecture. Okay. So what was the steps? I am writing step 7, that is convert in terms of f and eta, then integrate to get v. Okay, in terms of f and eta. So there you will get this. Okay, obviously here x is there, but you can convert this in terms of delta. Okay. Okay, so now let me remove this writing because I want the space to be clutter free. Now, so this becomes f dash into del t del x plus u infinity nu x, right, del t del y is equal to this. So what we do is we define a variable here theta, that is a function of eta. So here also, as I am using the same variables for u and v that was computed from the previous similarity solution, here also the similarity variable is eta. Okay, so eta was what? Y by delta, and delta was what? So delta by x was what? Rex whole to the power minus half, and that means delta was in the order of is into u infinity x by nu whole to the power minus half. That means, so nu by u infinity root and x and x, right? So see, I don't remember this form, but I can always derive this form, right? So what you can do is, you see that here you can take out this new, I mean I am just modifying this thing to get rid of x. So you can take out this new here, and you can multiply one new here and one new here, and then it becomes this, and you can take this new inside here, so it becomes nu into so nu by delta, because delta is the order of this. Okay, so and we also know that eta is this. So now I have converted this in terms of the similarity variable delta. Okay, so now theta of eta, that is equal to t minus t wall, t infinity minus t wall. I have defined it like this. Okay, and you can always define it by any other means. You have to just arrive to the solution. Even I think if you don't define theta like this, if you only work with t, then also you will get the solution. Okay, so this is just for the sake of non-dimensionalization, and we know that eta equal to y by nu x by u infinity. Okay, so that means now I have to convert this del t del x, del t del y, and del 2t del y square in terms of theta and eta. So that means del t del x is what? So del theta by del eta. Okay, so okay, so let us proceed step by step. So del theta del x into t infinity minus tw, and I have told that how this transformation comes, right? I mean why this t infinity minus tw came here. So that I will not explain now, because I have explained it ample amount of times before, and now this will be okay. So that becomes del theta, okay, not del theta, because theta is a function of sole function of eta. So this into this T infinity minus tw. So this will be theta dash into, okay, so d eta del eta del x, what will be that? Okay, so earlier we assumed this to be y into gx, so we could have write g here. So I have left that thing up to you to do it as a homework. But now we know the form of theta, so then here we know that del theta del x is what? It will be u infinity by nu y. So x to the power minus half is there, so minus half x to the power minus 3 by 2, right? So that will become minus half into y u infinity by nu, right? And 1x would be here, and x to the power half, and 1 by x would be here. So you can recognize this as, what, eta, right? Because it is 1 by, I mean the same thing, it is here. So this becomes what? Eta y by 2x minus. So if I am right, okay, eta y by 2x. Okay, so there is no y because y is absorbed here. So actually I have done these things before, a long ago, I admit, but still I know that what should be the form. Okay, okay, so now del theta del eta del x is this. So this will be what? This into, okay, minus this eta by 2x into t infinity minus t wall. Okay, now what is remaining? Del t del y in the same form, that will be del theta del y t infinity minus t wall, that will be d theta d eta into d eta dy t infinity minus t wall, that is equal to theta dash into, and what will be this? This will be just y, and now this will be this, sorry, u infinity by nu x, and here it will be the same thing, this. And now I also have to calculate this one. So this will be d dy of, that means d dy of the whole thing, that is theta dash t infinity minus t wall, and that will be nothing but what? That will be nothing but d d eta of this whole thing. I am doing this step by step for the sake of your understanding, into del eta del y, right? So here it will be theta double dash, because all these things are not the function of eta, right? And here del eta is again the same thing. So this turned out as this into t infinity minus t1. Now we have the forms. So let us put them one by one into the energy equation. So u into that, right? So u was what? U was f dash. So This was our actual energy equation. So let me cut it. Okay. Okay, so let me cut it here. Not cut it, let me paste it. Copy and paste it. Why it is not okay? Now it is here. Uh, okay, now it is fine. So now I have the form of del t del x, and that is what? This one. Sorry, that is this one, right? Minus theta dash eta by 2x, right? So this will be okay. So I am writing the whole equation minus theta dash eta by 2x t infinity minus t1 plus u infinity eta by x into half into this. Okay, so del t del y is what? Del t del y is this one, theta dash into u in. Okay, so theta dash into root over of u infinity by nu x t infinity minus t1. Okay, that is equal to alpha into this thing, theta double dash u infinity by nu x, this one. Okay, so now first of all see that this thing cancels out from all the side. Okay, so what remains is I'm writing each step with different colors so that things becomes easily visible. So this becomes this eta by 2x. Okay, so now just multiply these two. So u infinity, okay, nu and nu cancels out and by x, and 2 is there, and here it is eta f dash minus f theta dash, and so then it becomes alpha theta double dash u infinity nu x, and nothing is there. Okay, so see that this cancels out. Okay, so the next step becomes minus f dash theta dash by 2 plus u infinity by 2 into what? This minus f theta dash equal to alpha theta double dash u infinity by nu, right? So is it in the form of an ODE? Let us see that. Okay. Had I done a mistake, because there should be no u infinity? I think I have done a mistake. And what is that? That is, here u is not equal to f dash. It is f dash into, from here u is equal to f dash into u infinity, right? Okay. So here there should be a u infinity, and also there should be a u infinity, and also there should be a u infinity, right? Also there should be a u infinity. So see that u infinity is cancelling out this, this, and this. And now, do I have any other variable than eta f and theta dash? I mean eta f and theta? I think no. So now my equation becomes I think this is the final form, that is minus f dash this by 2 plus theta dash f dash eta by 2 minus f theta dash by 2 is equal to, okay, alpha by nu is 1 by Prandtl number and theta dash, and this cancels out, right? So my equation becomes theta double dash plus Prandtl number by 2 f theta dash, that is equal to 0. So see, I have converted the energy equation into an ODE. Okay, both theta and f are the functions of eta, but now I have two dependent variables f and theta, but I know the solution of f, so that is not a dependent variable. I mean that is not a unknown. Okay, so this is my similarity solution. I mean similarity, I mean the equation that I have got from the similarity variable. Okay, so now let me proceed. So I have two cases. One is Prandtl number much less than 1. So let me solve the first case, Prandtl number much greater than 1. Okay, so this is my first case. So for Prandtl number much greater than 1, okay, what I can do is, I know the solution of f, so f is not an unknown here, just keep this in your mind. So I can write this equation as what, del uh, okay, del theta dash d eta plus Prandtl number by 2 into f into theta dash. Okay, so then I have this by this equal to Prandtl number by 2f d eta. Then I have ln theta dash is equal to integration of Prandtl number by this, right? So plus c. So this is the constant of integration. Okay, first of all, there is when you write an ODE or PD or anything, you should write the boundary condition obviously. So that was a mistake by me. So this is a second order ODE. We need two boundary conditions. So boundary conditions, what will be those? So boundary condition 1 is at y equal to 0, t is equal to t wall. So let us look back to our theta. So theta is what, this. So if t equal to t wall, then this becomes t wall and theta becomes 0. So this boundary condition boils down to at eta equal to 0, theta is 0. Then we have at y equal to, or when y tends to infinity, at y tends to infinity, t is equal to t infinity. So let us again look back to our theta. So here if t equal to t infinity, then this theta becomes 1, right? So then it will be at eta tends to infinity, theta is tending to 1. We have these two boundary conditions, right? So this integration is from 0 to eta. Okay, so now if I put the same thing here, okay, and also we actually have another condition for theta dash, that is at y tends to infinity, del t del y is not changing, so this tends to 0. That means at this tending to infinity, theta dash will become 0. Okay, so now let us see that how can we find the c. Okay, so one thing we have that at eta equal to 0, okay, now we have to find, so this is the actually solution, but we have to find the C, right? So at eta tending to infinity, theta is equal to 1, that we know, right? And what we can do is, here we could have set the limit 0 here and eta here. So I am just recasting the equation. So this becomes theta dash of eta, okay, by theta dash of 0. So that is this, right? Okay, so there is a minus here. So it is now the same form, and this C is absorbed in the theta dash of 0, which is also an unknown and a constant. So C is absorbed here. I am just recasting this equation. So that means I have this d theta d eta as e to the power what, e to the power minus pr by 2f d eta 0 to eta into theta dash of 0, right? So then I have the solution as theta as, so theta as 0 to eta 0 to eta, right, into this d eta. So you should be in a state in which you can say that I am okay with all the mathematical steps. Unless you are okay with all the mathematical steps, it is not right. I mean, the learning is not complete. So just be clear with yourself. If you are not clear, you can always ask me in the comment section. Okay. So then, using the boundary condition that at eta tending to infinity, theta is equal to 1. Okay. So we know at eta tending to infinity, theta is equal to 1, and that means 1 is equal to this into theta dash 0 eta, right? And theta dash 0 is a constant. I can take it out from the integration. So theta dash 0 is 1 by this. This theta, right? So now I have the full solution, because if I put this theta dash 0 here, then I am getting the theta. So this is the formula for theta. Okay. So now I will calculate the Nusselt number, right? So I have told you, I have shown you that Nusselt number is nothing but the non-dimensional temperature gradient at the wall. Okay. So that becomes, okay, okay, so let me do it in another way, but this should also work. Nu x is hx by k, and that is the non-dimensional temperature gradient at the wall, is eta equal to 0, right? So this theta of 0, this will be the leading constant of the Nusselt number. Now Nusselt number, how I can get it, how I can get the actual value. So that is the, so this is the order of the Nusselt number, okay, that we will get, and we will see that if this order of the Nusselt number is same as the order of the, I mean that the order we got from the scaling analysis or not. Okay. So I know that at wall h into T infinity minus T wall, okay, that is equal to K into del T del y at y equal to 0. I mean, if it was T wall minus T infinity, then I have to put a minus here. Why? Because my wall is this, and if my y direction is this, so then the direction of the flux that is written by minus k dt dy, that has also a direction this, I mean in the positive y. So in this I have, if I have qy, so that is this, and which flux is going towards this, that is h into T wall minus T infinity, right? So if I am writing T wall minus infinity, then I have to put a minus here, okay. So then now if I non-dimensionalize this, T wall minus T infinity is equal to minus k del theta by del y into T wall minus T infinity, right? Or it was T infinity minus T wall, maybe. Let me see, T infinity minus T wall, right? In the definition of theta, I was having T infinity minus T wall. Okay, so this at y equal to 0, and again I can write h into T wall minus T infinity equal to minus k. Okay, so minus minus cancels out, and this becomes T wall minus T infinity into del theta, or directly, sorry, d theta d eta into del eta del y at eta equal to 0. So this becomes, okay, so this is cancelling out, and this becomes h equal to this at eta equal to 0, and del theta del y is nothing but 1 by delta, right? And so let me see. Okay, so it is a good practice, and I want to put it into your head, that is whenever you forget something like this, you always derive this. So I need 1 by delta, I should find delta, and that is x into Rex whole to the power minus half. So x into Rex means u infinity x by nu whole to the power minus half, that means nu x by u infinity whole to the power half. So I got the 1 by delta, that is u infinity by this. Okay, so I got this. Now what I have to do is this hx by k, so multiply by x with both side. So this is d theta d eta at eta equal to 0 is theta dash of 0. I have multiplied an x here, so it becomes e infinity x by nu. So this becomes what? Rex whole to the power half. And Paulhausen showed that this becomes, okay, for Prandtl number greater than 0.5, Paulhausen shows that this is 0.332 into Prandtl number whole to the power 1/3. So the Nusselt number based on x becomes theta dash of 0 into Rex root Rex, and that is 0.332 Prandtl number half, Prandtl number 1/3, and Rex whole to the power half. See, from the scaling analysis we got the same scale. Just let me show you this. Now we got the constant here. So here it is 0.332. So that we got from the similarity solution. Okay. And now let us do the next case quickly, because that is not very complex. So for Prandtl number much less than 1. So here we know that u by u infinity is almost equal to 1 for each point in the domain. So that means f dash is almost equal to 1. Okay. So if we get the main equation, that is theta dash plus pr by 2 into f into theta dash, that is equal to 0. So this was the ordinary differential equation that we got from the similarity solution. Okay, so here Now if I integrate it once more with respect to eta, so it becomes one more dash, this into f into theta double dash plus pr by 2 theta dash into f dash, right? So what we can do is, now, okay, I think this is not the approach. The approach should be this, because I want to put the value of f dash here. So I can write it like this, then I am doing it. The same thing you will get, but in a different way. I mean, this equation and this equation are, I mean, should be the same. If you simplify this one, you should get this one, but mathematically this will fulfill a purpose, the second one. So this will be pr by 2 into f dash. Now f dash is almost, f dash is 1 for almost every point in the domain for Prandtl number much less than 1. So this becomes theta dash d eta is equal to minus pr by 2. Okay. So now from here you can solve it. So that means this by theta dash is equal to minus pr by 2 d eta. Okay, and this is what? This is d theta dash by theta dash equal to, I mean, sorry, this you can write as d eta of theta dash by theta dash equal to pr by 2 d eta. Right? Okay, so this was, I had to integrate, and this was pr by 2 eta plus some c. Okay, and now I have it like this. So then d theta, this is equal to pr by 2 into eta square by 2 plus c eta plus c1, integration of this obviously. Then ln eta is this pr into eta square by 4 plus c eta plus c1, right? So now you have to put the boundary conditions. So let us write the boundary conditions here. So at eta equal to 0, I have theta equal to 0. I have written this earlier, so I am not explaining this again. So at eta is tending to infinity, theta will tend to 1, at eta is tending to infinity, theta dash will tend to 0. So we have these three, and now we have also one more boundary condition. So see, at eta equal to 0, f is the stream function I told, and I can take it as 0 at wall. So f is 0. So at eta equal to 0, this term goes to 0 as f is 0. So that means theta dash is equal to 0. So at eta equal to 0, theta double dash is equal to 0. And if you put this here, I mean here, okay, so this is what? Theta double dash. Okay, so if theta dash is finite, I mean at the wall theta dash cannot be 0. Okay, at least for this case. So theta dash is finite. Now at eta equal to 0, theta dash is also equal to 0. That means c is equal to 0. Okay, so this also is equal to 0. So that means I am having the equation as ln theta dash is equal to pr by 4 into eta square plus c1, and that is, so d theta d eta is equal to e to the power pr by 4 eta square into some a, where this a is nothing but e to the power c1. Okay, so now I have to find this a. So let me see that this eta, so this I can find this theta. So theta is what? Theta is e to the power pr by 4 eta square, a I can take out by d eta and 0 to eta. Okay, if you now integrate this, so I have to find this a. How can I find this a? I can use this boundary condition here. At eta tending to infinity, theta is equal to 1. So theta is equal to 1 for eta a equal to infinity. So pr by 4 e to the power eta square d eta. So now let me do some substitution, that is pr by 4 is equal to z, I mean pr by 4 into eta square. So that means pr by 4 into 2 eta d eta is equal to dz. That means, so this 2 and 4, this 2, so d eta is dz by, so 2 dz by pr by eta, and eta is what here? Eta is 4z by pr and its root, so 2 root z root pr, so that becomes dz by root pr and root z. So let us put it into this equation. So that means 1 equals to a into 0 to infinity e to the power z dz by root z root pr. So that means 1, okay, so here 1 equals to a by root pr and 0 to infinity e to the power z z to the power minus half, and minus half I can write minus 1 plus half. Okay, dz, let me put a line here, dz. So 1 equals to a by root pr, and if you can recognize this, this is gamma half, gamma function of half, and that is equal to root pi. Okay, so this is root pi, so that means a is equal to, so a is equal to, I am sorry for the barking of the dogs, I don't know that why they have started barking like this, but I am sorry for the disturbance. So a is equal to root over of pr by pi. Okay, so now I have completed my solution. So that means my theta is equal to root over of pr by pi. Okay, and this is 0 to eta e to the power this thing. And now this is, in terms of mathematics, this is called the error function of the argument pr to the power half by 2 eta. Okay, because you see that this is nothing but the square, I mean this thing is root pr by 2 into eta whole square. So it is the error function of this argument. Okay, so I have found out the theta, and okay, so and now, okay, so I have found out the solution for theta for both the cases of Prandtl number less than equal to 1, I mean much less than 1 and much greater than 1. Okay, and now similarly I have found out the theta. So similarly what you can do is nux is hx by k, and in the similar manner you can show that this will become this into pr to the power half into rex whole to the power half, and this is your homework. Okay, and what is your homework? You have to show that this is the theta 0. Okay, okay, you have to show that this is the theta 0, and just tell me that what is 1 by root pi. Okay, and what is 1 by root pi. So I don't have my calculator, so I am just using my phone to calculate that. Okay, um, and where is my calculator here? Actually, I don't use the calculator often, that is why I am not getting the calculator from the phone. So it is 1 by, okay, so okay, so let me do it right. 1 by root over of, where is pi? Yes. So this was the value of 1 by root pi. Okay. This is the value of 1 by root pi. So if you plug this thing, okay, so then you can find the theta dash also. So for the theta dash, you have this. You have already the expression of this. So theta dash of 0 is what? A. You can see theta dash of 0 is A, because if you put theta equal to 0, then it becomes A. So I just wanted to show you that this is the theta dash of 0, and here you can derive the value of that constant, that is the constant that was missing from the scaling analysis. So your homework is to show that NUX is equal to theta dash 0 into REX whole to the power half, and that we actually already have shown previously, but not seeing that part, you just try it by yourself by energy balance, that is H into T infinity minus Ty, that is equal to minus K del T del Y at Y equal to 0. I have told you almost the 90% part. You have to just non-dimensionalize this T to arrive NUX, that is equal to theta dash 0 into RX whole to the power half, and we know that theta dash 0 is nothing but A is root over of Prandtl number by pi, that is 0.564 whole to the power Prandtl number, sorry, 0.564 into Prandtl number whole to the power half. So what have you learned from this video? So I was also struggling to derive this because I have done it long time ago, but I know the basics. So I always say you, and these are the more important things, because if you keep these things in mind and build this type of mindset, then you will be unstoppable. That is, you should memorize the minimum things, but the most, I mean the strongest things. Okay, that is, for example, in fluid mechanics, if you remember the RTT, the Reynolds transport theorem, then you can derive almost any conservation equation. Okay, not almost, I mean any conservation equation. Okay, the basic step is RTT. Obviously there are another approaches, but following RTT you can do it in a very easy way. But if you, even if you don't remember RTT, you can always go by some uh, I mean you can always derive the RTT, because RTT is nothing but the conservation of a property, and it connects the Eulerian approach to the Lagrangian approach. So you should remember the least amount of things. You have noticed that I was forgetting every time the expression for delta, but I know that how delta is varying with x. I know that variation, so that is enough for any calculation. Okay, so, and I have also said that this similarity solution, the same thing I have done for the momentum. So you should be like, I mean, you should at least remember the that is what is similarity solution. That is, in any interview, if you are asked that what is similarity solution, you should convey your understanding, right? In forced convection, I mean in internal forced convection also, there are some solution in which you require the you require this similarity solution, and there also if you again ask that I don't know what is similarity solution, I knew that what is the solution for external force convection over a flat plate, but I don't know what is similarity solution, because that was the solution that was specific to that problem. I can do the solution for the external force problem, but now I have given you a new PDE and you are asked to solve for uh, this, and you know, and someone has told you that similarity solution will work here, and you should not be clueless there, because you have already solved two very important and very tough problem regarding the similarity solution. So now you should be comfortable with similarity solution after doing this two similarity solution, one for momentum and one for energy, by your own hand. Okay, so I hope you will do that. And you obviously put, if you I mean, put your suggestions and comments in the comment box. I will go all of through. Okay, I will go through all of them, and until then, bye bye and take care. And if you have any question in mind regarding anything, you can always post that. Thank you.